Alright, so let's take a look at another application of derivatives, and we're going to apply this to some vector quantities regarding motion, right? And this includes position, velocity, and acceleration. Now I'm going to let S of t represent position, right? So the position of an object in meters north, right? Because position, it is a vector quantity, you usually have to associate the object with a direction, right? So the position of the object in meters north relative to a point after, let's do t seconds. Okay, so the unit for position is going to be meters. Notice how we talked about displacement. Displacement is the change in position, so you can use this analogously, right? So the position, displacement is basically final position minus initial position. So we'll use this analogously in our description here. Now velocity is the rate of change of position, and when we looked at rates of change, we looked at the slope of, specifically the instantaneous rate of change, we looked at the slope of the tangent. Therefore, if the velocity is the rate of change of position, it goes to show that velocity is basically the first derivative of the position function. So we can write this using Lagrange's notation as s prime of t. In the case of Leibniz's notation, we can write this as ds relative to dt. Okay, so the rate of change of position relative to the rate of change of time. That's essentially what the Leibniz notation stands for. So velocity is the rate of change of position, right? So the first derivative of the position function will give us velocity. Then we also can describe acceleration, which is the rate of change of an object's velocity, sorry. And the rate of change of an object's velocity, a of t, is v prime of t, right? It's the derivative of the velocity function, and it can also be written as the second derivative of the position function. Now using Leibniz's notation, because it's the derivative of the velocity function, we can write this as dv over dt, right? The rate of change of velocity with respect to the rate of change of time. We can also write this in terms of the second derivative, and we can write this as the second derivative d2s of the position function relative to time, okay? So you can also write it in terms of Leibniz's notation like that. And in this sense, we want to describe. I want to describe an example relating the two. Now, I also mentioned here that acceleration can be combined with velocity in determining if an object is speeding up or slowing down, because we said that the acceleration is the change in velocity, right? So if the object acceleration accelerates in the same direction as the velocity, in the sense of a function, that means that they have the same sign, right? So if you multiply the velocity function times the acceleration function and it's greater than 0, that means that the object is speeding up, right? So another word for speeding up is accelerating, right? And acceleration is just the collective term that we use for change in velocity. In the other scenario, if the velocity function and the acceleration function have opposite signs, then we would say that the product of these guys would be less than 0 and the object would be slowing down or decelerating. So that means that the velocity vectors would essentially decrease over time. Okay, so this is a good way to kind of understand if an object is speeding up or slowing down. Now I'm just going to show you guys an example regarding the position function. We'll look at the first and second derivative to kind of identify the velocity and the acceleration function. So in the position function, I'm going to say an object's position can be modeled by maybe this equation, negative 5t squared plus 3t plus 2. Okay. Now the velocity function, v of t, is the first derivative of your position function, and I'm going to be employing the power rule as well as the sum and difference rules. Okay, so you're basically taking the derivative of all of these terms, right? So I'm doing negative 5 d dt of t squared plus 3 d dt of t plus the derivative of 2 with respect to dt. and that's going to give us 0, so derivative of any constant is 0, and then we get negative 10t plus 3. Okay, so this is our velocity function. It's the first derivative of the position function. If you want to find the acceleration function, right, it's the first derivative of the velocity function over the second derivative of the position function. What you're going to get here is I'm going to do the derivative of negative 10t plus the derivative of 3, which is a constant, which is 0, and the derivative of negative 10t with respect to dt is negative 10. So the acceleration is actually constant. When the acceleration is constant, this motion actually identifies something called uniformly accelerated motion. That's not really relevant in calculus, but it is a very important concept when you are studying projectile motion and basically physics in a sense, right? So in this case, the acceleration here is negative 10, and the units that we use for acceleration is meters per second squared. The units we use for velocity is going to be meters per second, and the units we use for position can be most commonly in meters. Okay, so that's an example of how we can compare the position function or displacement function to velocity and acceleration.